Well, hello and welcome everyone. Let's get things started for day 2 of Next. Let's start by a quick straw poll. Raise your hand if you ever had to build an ETL pipeline, which was largely copying data so that you can enable a business use case. Well, quite a few. Now, keep your hands up if you felt that after creating that pipeline, you increased the complexity of managing that data or security and governance. Well, quite a few. So that's really the crux of this session today. We will really be talking about how you can actually build a architecture that's predicated on a single copy lakehouse, one that allows you to make sense of all of your data with all analytics and AI engines, and do so in a secure, governed, and performant manner. My name is Gaurav Saxena. I'm a group product manager here at Google Cloud focused on lakehouse, AI, and analytics. And I have the pleasure of joining me today is Rohit Dewan, who is Chief Technology Officer for Rakuten's tech platform, who will be sharing insights and learnings from their lakehouse journey. So first of all, I do want to start off by saying that this is a super exciting time. We are at the dawn of generative AI, and there are lots of reasons that you might have heard why people are excited about this. But I want to point out 2 specific things that are very relevant to the lakehouse topic. Well, first of all, if you look at a typical enterprise today, we are only scratching the surface in terms of the percentage of data that's really recurring into value. And a large reason of that today is, if you look at businesses, today they generate a lot of data every time a support interaction happens, every time a customer leaves a feedback on an online platform or creates a video. That's a lot of unstructured or multimodal data that being created. The problem was that the tools to unlock that was very expensive. Well, now generative AI has the promise to solve that particular problem and really make sense of all your data. Second, the assistive technologies will help every data practitioner, each one of us, to do more. And this is why it's super excited that it needs to be kind of grounded in the context of your enterprise data. Well, and while a lot of focus has been on AI models, the heart of AI is data. And this is why many of you have been already thinking about these use cases or trying out these use cases today have been asking, how do I connect data to use cases easily? And to do so in a secure manner, governed manner, and to be able to do it without writing a lot of custom infrastructure. Let's talk about how a GCP lakehouse helps you achieve these things. So the biggest problem when it comes to connecting data to use cases is really the siloed nature of the data lake, the data warehouse, and the AI stack. Each layer in the stack has its own way to access data and its own way to manage metadata. Well, what this really means is if you are going to start up an AI project or an AI use case, and if that data is present in a warehouse, you will now write to have an ETL job to pull that data out. And as pointed out through a straw poll, that really becomes challenging. Well, that complexity only increases if that data is in different formats or in different clouds. Besides the security and governance challenges, all of these, the physics of moving the data really comes in the way. And while this is extremely painful for us data engineers, ultimately this slows down value generation. And we are today here to look at how we can really help this kind of use cases. Now, last year, to address some of these problems at this very conference, we announced BigLake. BigLake is a storage engine that unifies your data lake, warehouse, and AI workloads. It does so by providing a single fabric of data over which multiple engines can interact with and do so in a secure and governed manner. It abstracts and decouples some of the common shared infrastructure from query engines such as metadata and security and abstracts into a vectorized runtime on its own. This is what allows query engines to interface with all the data underneath spanning across formats and cloud boundaries and to be able to access that data with built-in fine-grained access control and also with price performance. Ever since the beginning of this year, we have seen a lot of growth with many of you building these lakehouses. In fact, processing over BigLake has really increased by 27x beginning of this year. And the first question that many of you are asking is, what table formats does BigLake support? Table formats have really taken off in the last 3 years because of the promise of providing rich data management capabilities over open format data. Apache Iceberg, Delta, or Hoodie are popular names. We have specifically seen a lot of interest in Apache Iceberg. And this is why I'm excited to share that the support for Apache Iceberg is now generally available in BigLake. You can create or modify an Iceberg table from open source engines such as Spark, and that table can automatically become available for your BigQuery users to go query and consume. This is made possible through a shared metastore architecture. BigLake Metastore is a shared metastore between open source engines and BigQuery, making it easy for you to access your open source tables directly in BigQuery and query it. When it comes to querying, BigQuery natively understands Iceberg metadata. And this is what makes it really easy for BigQuery to not only deliver a performant query experience, but to deliver it with full fine-grained access control model. BigLake enforces fine-grained access control over your Iceberg data and enforces it when you're querying from BigQuery, as well as from open source engines when you're going through the BigLake interface. This really makes sure that not only are you running open source Iceberg, but you are actually running in a secure manner, and you are running in a performant manner, and you are integrating all of the data which was already present in BigQuery or in other places. While Iceberg has dramatically accelerated the adoption of open lakehouses on Google Cloud, some of you have already been using Delta or Hoodie for your workloads for specific use cases. And this is why I'm also really excited to announce today that Delta and Hoodie is now supported through BigQuery manifest. You can now create a BigLake table by pointing to the manifest generated from Apache Hoodie or from Delta, and that table can now be queried from BigQuery. The manifest support now supports partitioning as well, which means we scan less data every time you're running queries against these open formats. Lastly, the same security model that we spoke about of Iceberg in context of fine-grained access control, all of those features also work on Delta as well as on Hoodie, which means you can either use BigQuery or open source engines to query these tables with row, column level access control or through dynamic data masking. Besides the support for table format, many of you also ask about query performance. It's really one of the chief characteristics when choosing a particular technology stack to run on. And performance has been an important area of focus for us. This is why what we have been doing is really expanding the underlying infrastructure that we've already used for BigQuery. It's called Big Metadata. That really represents rich metadata profile, now extended to open formats so that we can capture rich Parquet status and metadata and use that effectively for query planning. All of this has meant that on the TPCDS benchmark, we are now 4x faster than we were before on BigQuery external tables. And this increased performance, by the virtue of leveraging metadata, also means that we have to scan less data, reducing the cost of running these queries and posing a 75% reduction when compared to BigQuery external tables. So if you are running BigQuery external tables today, it's really a no-brainer to upgrade those to BigLake tables and get better performance, lower cost, and fine-grained access control for your workloads. Put together, these tools will really help you connect more of your data and more of your formats and across clouds to more use cases and really help advance the development of analytics and AI. Now, another big area that keeps coming up all the time is that many of you have said that we really want to pursue an open format strategy. And reasons range from long-term vendor neutrality or being compatible or interoperable with multi-cloud or hybrid architectures. A single format can make that easy. But management of data is painful. You have to ride a lot of these background jobs to constantly optimize file sizes, garbage collect, or be able to do features that will optimize your overall query performance and impact the TCO of your overall workload. This is why, and this particular problem also gets even more complex when you are doing use cases like high throughput streaming, change data capture, which results into the dreaded small file problem that really ends up impacting query performance and requires a lot more infrastructure maintenance and management to just keep the workload really running in a performant manner. Specifically, when there are use cases like GDPR, which often require you to perform deletion operations at a granular level, those becomes really expensive because The open formats are really modifying multiple files, and the atomicity could be a batch of files. So these are some of the challenges that many have been asking, and they are solvable, but they require a lot of work. That creates infrastructure. So I'm super thrilled to announce something special that we've been working on over the course of last year. It's called BigLake Managed Tables that provides a fully managed lakehouse experience for your open format data. It provides DML and transactions on your Parquet workloads for your data residing in your cloud storage buckets. It provides a fully managed lakehouse experience with automatic background storage optimizations, such as file compaction and garbage collection, to help you make sure that you are running optimal performance and cost. And it provides an interface to do extremely high throughput streaming ingestion that scales to tens of gigabytes for the most demanding workloads, paving the way for CDC and other advanced analytics use cases that you can now run on open format data. The key underlying principle for us has been openness, where data stays in your buckets and it's managed in open formats. All of this is enabled in a fully open architecture by building in full compatibility with Iceberg. BigLake Managed Tables provide Iceberg metadata so that your open source engines can query it just like if they were querying Iceberg tables. BigLake Managed Tables really brings the best of Google managed storage management infrastructure that has already been tested at massive scale with BigQuery and innovates on it to make it optimized and work on your open format data. We are very excited about this. There are three key ways in which you can use BigLake Managed Tables. Let me start by calling those out. First one, you can use BigQuery to perform DML ingestion into your tables, just like you would do on a BigQuery native table. And then BigLake will actually perform all of these underlying data management operations, such as file compaction, auto clustering, clustering of data, automatic reclustering, as well as garbage collection, to make sure that you don't have to write these infrastructure tasks and you still get a very performant experience at the right price point. If you are building streaming pipelines, that's the second use case, where you can now use the BigQuery Write API to actually write data to these tables using connectors from popular open source engines like Spark, or just build your own client library-based connectors to write it from your own custom engines. And this really scales to several gigabits per second. Part of the reason why this becomes possible is that historically, when you are building high throughput streaming pipelines, you are constrained by the write throughput from object stores or the transactions on the open formats. BigLake Managed Tables take an approach where ingestion is first written into a write optimized storage that is massively parallelized, and then it's converted into Parquet, into columnar. This really allows ingestion to really scale up to extremely high limits for the most demanding workloads, but yet provide you zero read stillness. Your queries actually merge the data between Parquet as well as the write optimized store to make sure there is no latency when you're querying the results. And then files, the small files are automatically compacted in optimal manner to ensure the best performance. And third is that you can now also use open source engines to query these tables via the Iceberg snapshots, and the BigLake's zero trust security model of find and access control also applies in these use cases. So these are just some of the ways we are already seeing customers build capabilities around this. And with that, let me invite Rohit from Rakuten to share a little bit more about their journey on Lakehouse and key learnings from it.
Thank you, Gaurav. And thank you for sharing with us the exciting features of BigLake. So my name is Rohit Dewan. I am the CTO of the platforms group at Rakuten. And so while Gaurav talked about all the features of BigLake, I wanted to get more into kind of our motivations around moving towards a lakehouse architecture and some of the considerations we had in choosing BigLake. So Rakuten is a pretty fascinating company. We were actually founded back in 1997 as the first e-commerce marketplace in Japan. And starting in the early 2000s, we started to diversify into credit card, travel, other fintech businesses. And kind of fast forward to today, we're a conglomerate of more than 70 businesses that connect together in an ecosystem through a common membership and a common rewards program known as Super Points. If you're in Japan, you pretty much can't miss us. I mean, almost 0.3% of Japan GDP goes through Rakuten in some way. So we had almost, I think, last year, about 34 trillion Japanese yen in transaction volume. And so as you can imagine, we have pretty much very incredible breadth and depth of data. So we have I mean, you can see our mission statement up there. I imagine many of you in your data platform organizations have something similar. But this kind of simple mission hides a lot of complexity behind it. So one is just a sheer number of users. We have more than 2,000 data analysts, hundreds of data engineers, hundreds of data scientists, and also as a global ecosystem company, we have dozens of people who are working on governance, audit, security, making sure we're compliant with GDPR, CCPA, and the variety of kind of data protection regimes around the world. Many acquisitions also means that we're de facto multi-cloud. So we're using all the major hyperscalers, and we're global as well. So at our level of complexity, I think one of the key considerations is that any core data platform process needs to be automated, because any manual step simply would not scale at our level. So starting at about 2000, we started on our, I'd say, data platform modernization journey. And back then, we were actually a purely kind of on-premise system. But as a very data-driven organization, the pressure on that system was growing very, very rapidly. I think at some point, we're looking at 1 or 2% growth per week, which compounded is absolutely massive. So in order to achieve kind of more elasticity and scale, we decided to move towards a hybrid data platform. And so as of last year, so this is October of last year, we are now fully hybrid. So we have our data both on-premise as well as on GCP. Now, of course, this comes with its own set of challenges. We move from just having, say, object storage and Hadoop on-prem to now also having data replicas in GCS, and also copying that over into BigQuery storage as well. So from a governance perspective, this is increasing our load, because we need to make sure that permissions are aligned across all these different systems. At the same time, from a data engineering or scientist perspective, there's a long time to get value from that data. So once data was produced, we need to run pretty heavy ETL jobs now to copy it into, say, BigQuery, where the bulk of our users were then going to consume it. So there might be like several hours or more of delay to get that time to value. And additionally, we had to, as we made copies through these replicas, we needed to be able to monitor quality to make sure that the copies are available and consistent across each replica, which is much more complicated than it sounds. So this was kind of real motivation to say we should consider a lakehouse architecture. So fast forward to today, and so we were one of the early launch partners for BigLake, and we've been able to reduce our number of data replicas in half. So on-prem, we're moving to just object storage, and on GCP, we're able to keep all our data within GCS, and for the most part, not have to copy that into BQ storage. So this is, of course, now reducing the time to data. It also simplifies our governance and access, because our governance teams can set policies essentially in one place and have them apply to our data, whether it be on-prem, whether it be on GCP, in AWS, or Azure. In addition, kind of all consumption can go through BigLake as well. So there are BigLake connectors for all the popular query interfaces, at least the ones that we use, like BQ and Trino. I should mention, we also have very significant cross-use of data, and that makes our governance even more complicated. But definitely moving to BigLake has helped us to simplify that significantly. So as we were making this journey to Lakehouse, these were, I'd say, the 5 kind of primary considerations we had. So one was performance. So we were definitely concerned that moving to not having data in BigQuery storage would lead to a significant reduction in performance. However, in our testing, we found that if metadata caching is turned on, the performance nearly approached, so I'd say like 98, 99% approached the native performance if that data were in BQ storage. We wanted to have fewer copies of data, and definitely that's something we were able to achieve with BigLake as well, and so getting much faster and real-time insights. We're able to set policies in one place, so definitely it's our CISO is having fewer sleepless nights as we are as well. Iceberg support is something that was important to us. I think as a company, we believe that's going to be the standard format going forward. And so in a future phase, probably later this year, we'll also be taking advantage of the Iceberg support that's part of the BigLake ecosystem. So net, I think BigLake meets all these considerations and has helped us to kind of achieve the next step in our lakehouse journey. I definitely wish you all the best in your next step. I mean, so many of you showed up for an 8 a.m. session, which tells me a lot of you are thinking about this topic as well. I won't be present during the Q&A, but I will hang around for some minutes after the session to answer any questions you might have. Thank you so much for your time. Let me pass back to Gaurav.
Continued partnership. Well, Rohit mentioned a lot about how getting to a lakehouse simplified their overall data architecture and really enabled many personas to come together and consume that single copy of data. Now, as many of you have been talking about lakehouses, one of the big challenges that we've been already hearing a lot is that how do we solve the data problem of the AI? And let me explain what I mean by that. There's a lot of value that many of our customers are exploring in the foundation models. But to really make it relevant and really work for their enterprise use cases, it needs to be grounded in their data. It not only needs to be grounded in their data, but it needs to happen in a manner that's secure, governed, private, and do all of that in a manner that does not really blow up price performance. So how do you really do AI in a scalable manner by bringing your own data with security and governance that's already built in, that you've already curated? And this is where the big lakehouse opportunity is to really simplify those challenges for you. So we mentioned that the analytics and AI lakehouse has for long been siloed, where analytics has largely focused on the structured data, but then AI, especially generative AI, which is now unlocking all this value from unstructured data, had almost like a separate path to get to the public cloud object stores where this data is largely stored. So the challenge we asked to the team back is how do we help customers get access to their data using the tools that they are already familiar with, using the governance frameworks that they are already using. And this is why I'm really excited to announce the general availability of object tables. Object tables are a layer on top of public cloud object stores. They represent metadata of underlying files that are stored in public cloud buckets, and they're a special kind of table, because they have the ability to actually retrieve the underlying object and serve it to the processing engine to run AI computation on top of it. These object tables are also really simplified to develop pipelines. When you add new objects to the pipeline, let's say new images got added to a bucket, the table automatically updates and really simplifies end-to-end development of AI pipelines. And finally, object tables enforce BigLake's fine-grained security model, which means if you are securing a specific row in the object table, you are actually securing the underlying image and the retrieval of that image that can happen to the signed URL. These capabilities make it really easy to build these use cases. Let me give you some examples of use cases today that we are seeing. Well, first up, a lot of companies today, as they are building their own versions of enterprise LLMs or fine-tuning foundation models to build their own versions, are first needing to do pre-training. This is where we care about how do you actually take the data that you have collected from various sources in object store like GCS, but still be able to transform it, parse it, or be able to filter out for things like opt-outs or training license rights which is largely stored in structured tables or it's extracted from this data. Through BigQuery object tables, you can now join object tables with rest of your other BigQuery tables, where you can write simple expressive SQL statements that help you curate your training corpus for this fine training to happen. This makes it really, really simple that otherwise would take a lot of coding to develop. The other thing that we are already seeing is once you actually get to a model, how do you know that it's really safe for your use cases? How do you know it's really high quality and giving good responses? This is where you can create object tables and call that model directly using BigQuery, whether it's hosted in Vertex or whether it's hosted and managed by you on your own custom infrastructure through a few lines of SQL. We are already seeing examples where customers are creating this object table over images and then using BigQuery SQL to call Vision API to figure out safety elements of the image and then be able to take action on it. One of the actions is really how do you actually secure specific PII objects if you detect specific metadata. And you can then cut off that access to specific groups or user admin personas to be able to make sure that the AI development that you are doing is consistent with the governance policies that you have described for your own organization. We're now taking these capabilities one step further, where if you think about the documents use cases, a lot of data, whether it's PDF files or text files, resides in object stores. Well, now you can use Document AI Workbench, and with just a few clicks, you can train a custom LLM extractor to extract specific things asked from the document. You can ask a question to really figure out what specific fields and schema you want to define for your extraction, and that's created. That really generates a API endpoint that gets deployed. Well, that API can now be called using BigQuery remote models. You can simply register that remote model in BigQuery with SQL and write SQL on object tables on PDF files to be able to invoke that API and then be able to extract text from the documents. Fine-grained access control, like I said, is already baked into the framework, so you can really control if you want to secure access to specific documents that contain sensitive information or PI information. Well, you can then build document analytics in BigQuery by combining with the rest of your structured data. Or you can also do other many interesting things with it. We are seeing opportunities to take that extracted text in BigQuery, and with the latest capabilities that we announced yesterday on embedding generation, you can now generate embeddings on those text columns. That embedding and index can then be synced to the Vertex matching engine, where you can actually leverage vector search to implement your enterprise LLM chatbots that is grounded in your data to implement techniques like retrieval augmented generation. And all of these capabilities make it really, really simple with few lines of SQL to bring your data to make custom-tuned LLM applications and to do it by preserving security and privacy in a governed manner. So I'm really excited with all the capabilities that we shared with you today and the experience from Rohit and his team to help you kind of build these lake houses. And we can't wait to see how you'll actually build in your own journey.